Hello everyone, myself Dr. Sunny Kumar. I am an assistant professor in Department of Chemical Engineering, PKG College of Engineering and Technology, Panipat. Today we are discussing about the Chemical Engineering Thermodynamics 1. This is a lecture 3. So in the previous lecture we have discussed about intensive and extensive properties, the state and path function, force, pressure and energy, and examples of its. So where we have described how the pressure acting when the force is acting on a surface perpendicularly, and what is the effect of heat, and how to generally store the energy. They may be the potential energy or kinetic energy. I have by the examples we have described this. So now today we will discuss about the equilibrium state and the phase rule. And the reversible and irreversible process and its examples. So if we will discuss about the equilibrium state, so when this you are seeing, this is an unstable system. Suppose when when it will be in horizontal direction, so it will be the equilibrium in state. This is another. So the equilibrium is a word which is denoting a static condition, the absence of changes. There is no changes further. So if you were seeing this example, so these are, there is a changes is happening. When they are stopped in a particular condition, then it will be the equilibrium state. So this is another examples here is given. So the in thermodynamics, it means not the absence of changes but the absence of any tendency towards changes on a macroscopic scale, because any tendency towards changes is caused by a driving force of any kind or another. The absence of such a tendency indicates also the absence of any driving force. Hence, for a system at equilibrium, all forces are in exact balance. So there is the forces are in balance. So if you will see this in example, this is a chemical equilibrium bridge. This is the time versus concentration graph. When this initial and this is a reactant NO2 which is decreasing with the time, but at a particular time there is no changes in this concentration of this NO2. But when you will seeing this N2O4, it is initially increasing, but after some time it is also reaching in equilibrium. So this state is called the chemical equilibrium conditions. So these are the two examples of equilibrium. So if you will see this example, there is this is a membrane. This dotted line is like a membrane, and these are some particles. This is molecules die. When after some time some molecule dye is passing through this membrane, but after some time they reach an equilibrium condition. There is no further changes in the dye molecules are not passing through this membrane. So this condition is called the equilibrium condition. So the imbalance of mechanical force such as pressure on a piston tends to cause a energy transfer as work. So there may be the mechanical equilibrium can be happens. So temperature difference tends to cause the flow of heat. The difference in chemical potential and tends to cause substance to be transferred from one phase to another. And at equilibrium all such forces are in balance. For example, a mixture of hydrogen and oxygen at ordinary condition is not in chemical equilibrium, because of the large driving force for the formation of water. However, if chemical reaction is not initiated This system may exist in longer term of thermomechanical equilibrium and purely physical process, and may be analyzed without regard to possible chemical reaction. So, and this is an example. If something is happening, the reaction is happening, so after a particular time, this graph we have already discussed in the previous slide. So now we have discussed about the different type of equilibriums that can be the mechanical based or for thermal based and chemical potential based. These are some examples we have given. Now I will talk about the phase rule. The phase rule, the state of pure homogeneous fluid is fixed whenever two intensive thermodynamics properties are set at a specific value. In contrast, when the two phases of the system pure species are in equilibrium, the state of the system is fixed when only the single property is specified. For example, a system of steam and liquid water in equilibrium at 101.33 kilopascal and 100 degrees centigrade. The temperature at a specific temperature pressure, they are in equilibrium for the water case because the phase is 1. It is possible to change the temperature without also changing the pressure if equilibrium between vapor and liquid phases is to be maintained. There is a single independent variable. So another system, when there is a multi-phase system at equilibrium, the number of independent variables that must be arbitrary fixed to establish its intensive state is called number of degree of freedom of the system, and this is number is given by the phase rule of J. Willard Gibbs. So if first time he has described this. So that is the non-reacting system. So this is a equation which is described as Willard Gibbs. So where f is the number of degree of freedom and pi is the number of phases and n is the number of chemical species present in the system. So this is a Willard Gibbs who described this non-reacting system. So the intensive state of the system at equilibrium is established when its temperature, pressure and the composition of all phases are fixed. So these are the properties, the temperature, pressure and composition, which are fixed. So they are variables of the phases rules, but they are not all independent. The phases rules which gives the number of variables from the set, this must be specified to fix all remaining intensive variables and thus intensive state of the system. A phase is a homogeneous region of matter, a gas or a mixture of gases, a liquid or liquid solution and a crystalline solid are example of phases. And abrupt changes in properties always occur at the boundary between phases. Various phases can coexist, but they must be in equilibrium for the phase rule to apply. A phase need not be continuous. An example of discontinuous phases are a gas dispersed as bubble in a liquid, a liquid dispersed as droplet in the another liquid with which is immiscible, and solid crystal dispersed in the either gas or solid liquid. So there are the two phases, the solid one phase and the another is gas, so they are not continuous. So in each cases the dispersed phase is distributed throughout a continuous phase and they are distributed in the this. For example, the phase rule may be applied to an aqueous solution of ethanol in a equilibrium with its vapor. So there is a two phase, the component are two, n equal to 2, there is a ethanol, and this is one the water, because it is aqueous solution. So there is a two species, and the phases are to be one is vapor and another is liquid. So if you will put in this equation this non-reacting phase rule equation, so you will get the 2, the degree of freedom will be the 2. So the system has vapor liquid equilibrium and it has 2 degree of freedom. So if the system exists at a specified temperature and pressure, assuming this is a possible, its liquid and vapor phase composition are fixed. By these conditions, a more common specification is of temperature and the liquid phase composition, in which case pressure and vapor phase composition are fixed. The minimum number of degree of freedom for any system is 0. When degree of freedom is 0, the system invariant, so the equation becomes pi equal to 2 plus n. The value of pi is the maximum number of phases that can coexist at equilibrium for a system containing n chemical species. When n equal to 1, so this limit is reaches for pi equal to 3, characteristic of triple point. So this is a characteristic triple point when the is a three phase is exists like solid, liquid and gas. So that is a triple point that we will read in further lectures. The triple point of H2O, where liquid, vapor and the common form of ice exists either in together in equilibrium, occurs at 0.01 degree centigrade and 0.0061 bar. So this in this condition that equilibrium happens. Any changes from these conditions causes at least one phase to disappear. For example, so how many phases rules variables must be specified to fix the thermodynamics state of each of the following system: liquid water in equilibrium with its vapor, and the second is liquid water in equilibrium with mixture of water vapor and nitrogen, and in the third case a three phases system. The first is only the one phase, two phase. Now it is a three phases system, saturated aqueous salt solution and its boiling points with the excess salt crystal present. So these are the three conditions are given and we have to solve, we have to calculate the degree of freedom of these systems. So the solution is, if you in the first condition the liquid water in equilibrium with its vapor, so there is a two phases, the one is liquid and another is vapor, and the chemical species is one which is water and it has two phases. So now you will put in this degree of freedom equation 2 minus pi plus n, you will get 1. This result is in agreement with the fact that for a given pressure water has but one boiling point, it has one boiling point. The temperature or pressure but not both may be specified for the system comprised of water in equilibrium with its vapor. So the two chemical species are present, again there are two phases. So this is the equation 2 minus pi plus n equal to 2 minus 2 plus 2. So you will get the degree of freedom is 2. So the addition of an inert gas to a system of water in equilibrium with its vapor changes the characteristic of the system. So now the temperature and pressure may be independent varied, but once they are fixed, the system described can exist in the equilibrium only a particular composition of vapor phase, because nitrogen is considerable negligible in soluble with water, or liquid phase is pure water. water. For the in another one, there is a three phase because the crystalline salts, saturated aqueous solution, and vapor. So there is a three phase. The solid, the crystalline salt is solid, and this is a liquid, and this is vapor at the boiling point. The chemical species n equal to 2. There is a 2, the salt and water only. For this system, if you will put in this phase rule equation, so you will get degree of freedom will be 1. So this is the example for the phase rule. Now we will discuss about the reversible process. The development of thermodynamics is facilitated by the introduction of a special kind of closed system process characterized as reversible. A process is reversible when its direction can be reversed at any point by an infinitesimal changes in external condition. So these are the, this is the example. So 1 to 2 and 2 to 1. So that will be the, so suppose there is a changes from 1 to 2. So if it is not further changed to 2 to 1, it now happens, so it will be the reversible. When it happens to the 2 to 1, so it will be the reversible system. So this is the thing. So one is starting like this, and it will be end like this. So initial condition, after some time it will reached, so it will be a reversible system. So this is a gas chamber, so it can also act as a reversible system. So this is the expansion of gas. The nature of reversible process is illustrated the expansion of gas, because when you initially gas is compressed, and when you will put a force on this gas, they are the molecules are close together. The system is go down, but when you release that pressure, so it will be attain the same position. So the another is the reversible chemical reaction. So that is a physical system. There is only the by the mechanical way we are changing the composition of solid calcium carbonate to form a solid calcium oxide and carbon dioxide gas. At equilibrium, this system exerts a specific composition pressure of CO2 for a given temperature. So this is a system. This is a calcium carbonate plus CaO, and CO2 is formed. The chemical reaction is held in balance by the pressure of the CO2. Any changes of condition, however, they slight upset the equilibrium and the cause the reactions to proceed in direction or the other. So now we will compare with the reversible process and irreversible process. The process is carried out infinitely slow, that is a reversible, but this irreversible process is rapid, and at any state the equilibrium is not disturbed. The equilibrium may exist only after the completion of the process, and it takes infinite time for the completion, and it takes a finite time for completion for the irreversible process. Work obtained in process is maximum, and work obtained in the process is not maximum. So this is an example of reversible process, and the initial stage after some time reach the same position. So this is the irreversible example, because we know that generally heat transfer happens from hot to cold, not cold to hot. So that is a best example for the irreversibility. So these are the examples and the differences between the reversibility and the irreversibility process. So if we will summarize this reversible process, a reversible process can be reversed at any point by infinitesimal changes, and external condition is never more than minutely removed from the equilibrium, traverse a succession of equilibrium state, is frictionless, is driven by force whose imbalance is infinitesimal in magnitude, proceeds infinitely slowly, when reverse retract its path, restoring the initial state of the system and surroundings. So these are the conditions generally happens for the reversible process. So now we will do some examples for the reversible process. Suppose a horizontal piston cylinder arrangement is placed in a constant temperature bath. The piston slides in the cylinder with negligible friction. There is no friction is happening, and the external force holds it in a place against an initial gas pressure of 14 bar. The initial gas volume is 0.03 meter cube. The external force on the piston is reduced gradually, and the gas expands isothermally as its volume doubles. So the volume becomes doubles. If the volume of the gas is related to its pressure, so this PVT, the pressure and volume, is constant at a given temperature. So what is the work done by the gas in moving the external force? What is the work done by the gas is moving the external force? So the process as described is mechanically reversible. If PV equal to K, so this is a van der Waals equation. So PV at constant temperature, so P equal to K upon V. So when you will rearrange this, so this is specifying the path of the process and leads to, so we know the work done. So this is we have in the last lecture we have studied. So when the at a different time, so when the volume is changing, so work done will be when you will integrate V1 to V2, so it will be minus K V1 to V2 d Vt Vt K ln V2 V1. The value of K is given by K equal to PVT and P1 V1. So the we have already given the pressure, which is 14 bar is given, which is 14 into 10 power 5 Pascal, and the volume is also given, which is 0.03 meter cube. So you will get this value of K will be 42,000 joule. So the initial volume we know, and the final volume we also know, 0.06 after the expansion. So the work done will, by if you will put the value in this formula, so W equal to minus K ln V2 upon V1, so you will get minus 29,112 joules, you will get it. So this is the work done, which done, and the final pressure will be P2 equal to K1 upon V2. So the the value of K we know, and V2 will be we know, so you can get the 7 bar, around the 7 bar the final pressure will be. So for this process the efficiency is around 80%. So we know that the efficiency is when 80%. So we could multiply the reversible work by this figure to we get estimate the reversible work. So you will get, when you will multiply the 80% to this work, so you will get minus 23,290 joule, you will get it. So this will be the 80% work done, which is done by this process. So in this lecture, in today's lecture, we have discussed about the equilibrium state and the phase rules, how many type of phases, and the system is dependent upon the in the phase rule we have discussed about the degree of freedom, and which is dependent upon the number of species and the phases, and reversible and irreversible process and examples of it, which system is reversible and how and reversible. And so this is the example of this we have discussed, and we have also described the non-reacting rules, which is given by the Gibbs. And this is the equilibrium condition. This is non-equilibrium condition when it is in horizontal, so it will be the equilibrium condition. So in the next lecture we will discuss about the internal energy and first law of thermodynamics for the cycling process and first law of thermodynamics for non-flow process. Okay, so thank you very much. So if you have any doubt, so you can ask me on this email, the chemicalsuniraj@gmail.com, and this is my website. So thank you very much.